Tonight, we're going to talk about the largest star ever discovered. A star so enormous that if you could somehow be transported to where our Sun sits, its glowing surface would stretch past the orbit of Saturn. The inner planets, Mercury, Venus, Earth, Mars, even the giant Jupiter, all of them would find themselves deep inside this star's outer atmosphere. By the end of tonight, you're going to see how we discovered a star barely holding itself together against its own light, why it sits at the edge of what nature allows, and how it reshaped everything we thought we knew about the true limits of stellar size. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The year was 1990. Astronomer Charles Bruce Stephenson was conducting a systematic survey of the sky, searching for massive star clusters hidden in the dusty regions of our galaxy. He was looking in the constellation Scutum, a small, faint constellation in the southern sky that sits right in the plane of the Milky Way. This region is crowded with stars, gas, and dust. It's one of those areas where the Milky Way appears particularly dense and bright, but also particularly obscured. All that dust makes it incredibly difficult to see what's actually there. Using infrared observations, which can penetrate dust better than visible light, Stephenson identified a cluster of stars roughly 19,000 light-years from Earth. It wasn't just any cluster. This cluster contained some of the most massive, most luminous stars he'd ever seen. Red supergiants, blue supergiants, stars pumping out hundreds of thousands of times more energy than our Sun. The cluster became known as Stephenson 2, and for years it remained an interesting but relatively obscure object in astronomical catalogues, just another massive young cluster among thousands in our galaxy. But as infrared astronomy advanced through the 1990s and 2000s, as new space telescopes like Spitzer and Herschel came online, astronomers began to look at Stephenson 2 more carefully, and they started to realize something remarkable. One star in particular stood out. It was incredibly bright in the infrared, far brighter than it should be for a normal red supergiant. It was so bright that it suggested either the star was much closer than the rest of the cluster, which seemed unlikely, or it was extraordinarily large. They designated it Stephenson 218, the 18th star catalogued in the cluster. Nobody at the time realized they were looking at potentially the largest star ever discovered. That realization came later as astronomers began the painstaking work of actually measuring the star's properties. And here's where the challenge begins. How do you measure a star that is 19,000 light-years away? You can't send a probe there. You can't get a close-up image. You're working with photons of light that have been traveling through space for 19,000 years. Light that left this star around the time humans were still living in small hunter-gatherer groups. Long before the pyramids were built, long before writing or agriculture or civilization, those ancient photons finally arrive at our telescopes, and from them we have to reconstruct everything about this distant star. Its temperature, its brightness, its size, its mass, its composition, all from light. The first step is measuring brightness. This is relatively straightforward. You point a telescope at the star, collect its light, and measure how much energy you're receiving. This gives you what is called apparent magnitude, how bright the star appears from Earth. For Stephenson 218, that apparent magnitude is fairly faint. You can't see it with the naked eye. Even through a small telescope, it's easily lost among thousands of other stars in that crowded region. But infrared telescopes revealed it's actually quite bright in the infrared, much brighter than in visible light. This makes sense for a cool star. Cool stars emit most of their energy as infrared radiation rather than visible light. Next, you need distance. Brightness alone doesn't tell you much because a faint nearby star and a bright distant star can appear equally bright from Earth. You need to know how far away the star is to calculate its actual intrinsic brightness, what astronomers call luminosity. For stars within a few thousand light-years, astronomers can use parallax. As Earth orbits the Sun, nearby stars appear to shift position slightly against the background of more distant stars. By measuring this tiny shift, you can triangulate the distance using basic geometry. But parallax only works for relatively nearby stars. At 19,000 light-years, the shift is far too small to measure, even with space telescopes. So, astronomers use other methods. Since Stephenson 218 is part of a cluster, they can estimate the cluster's distance by studying the cluster as a whole. By measuring the properties of multiple stars in the cluster and comparing them to theoretical models, they can bracket the distance. Different methods give slightly different answers, which is why distance estimates for Stephenson 2 range from about 17,000 to 20,000 light-years. Let's use 19,000 as our best estimate. Now, with brightness and distance, you can calculate luminosity. How much total energy is the star actually emitting per second? The calculation revealed something stunning. Stephenson 218 has a luminosity roughly 440,000 times greater than our Sun. Every second, this star pumps out 440,000 times more energy than our Sun does. That's an almost incomprehensible amount of power. But luminosity alone doesn't tell you size. A small, hot star can be very luminous. A large, cool star can also be very luminous. To figure out size, you need temperature. This is where spectroscopy comes in. By splitting the star's light into a spectrum and analyzing which wavelengths are present, astronomers can determine the star's surface temperature. Different temperatures produce different spectral signatures. Hot stars show different absorption lines than cool stars. The spectrum of Stephenson 218 revealed something immediately obvious. This is a cool star, very cool. The surface temperature is only about 3,600 Kelvin, which translates to about 6,000 degrees Fahrenheit. That might sound hot, and it is by everyday standards, but it's actually cool for a star. Our Sun's surface is about 5,770 Kelvin, over 10,000 degrees Fahrenheit. So, Stephenson 218 is cooler than our Sun. This is why it glows red. Cool stars are red. Hot stars are blue or white. The spectrum also revealed the presence of molecules in the star's atmosphere. Titanium oxide, water vapor, carbon monoxide. These molecules can only exist at relatively cool temperatures. In hotter stars, they would be ripped apart. Their presence confirmed this is a cool hypergiant. Now comes the crucial calculation. If you know how much total energy a star emits, its luminosity, and you know its surface temperature, you can calculate how large it must be. This uses a relationship called the Stefan-Boltzmann law. The law says that the total energy a star emits depends on two things: how hot its surface is, as hotter surfaces radiate more energy per unit area, and how much surface area it has. A cool star with enormous luminosity must have an enormous surface area to emit that much energy. When astronomers plugged in the numbers for Stephenson 218, the result was staggering. The star's radius came out to roughly 2,000 to 2,400 times the radius of our Sun. Let me put that in perspective. Our Sun's radius is about 433,000 miles. Multiply that by 2,000, and you get a radius of roughly 930 million miles. miles. That's the distance from the star's center to its surface. The diameter, the distance across, is about 1,860,000,000 miles. Stephenson 218 is the largest star ever discovered in the known universe. And now that you know how astronomers found it and measured it, let's explore what that actually means. 930 million miles in radius. That number is so large, it's almost meaningless without context. So let's try to visualize it. If you could somehow replace our Sun with Stephenson 218, keeping everything else in the solar system the same, here's what would happen. The star's center would sit where the Sun's center currently sits. But instead of the Sun's surface being 433,000 miles from the center, Stephenson 218's surface would extend to approximately 10 astronomical units from the center. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So this star's surface would sit at 10 times that distance. Mercury orbits at about 0.4 astronomical units. It would be deep inside the star, completely engulfed. Venus at 0.7 astronomical units, also inside. Earth at 1 astronomical unit, the distance we use as our measuring stick, would be nowhere near the surface. We would be deep within the star's outer envelope. Mars at 1.5 astronomical units inside. The asteroid belt between 2 and 3 astronomical units, entirely contained within the star. Jupiter, the largest planet in our solar system, orbits at about 5.2 astronomical units. Even mighty Jupiter would find itself within the star's glowing atmosphere. Saturn, the ringed giant, orbits at about 9.5 astronomical units. Stephenson 218's surface would extend past Saturn's orbit. If you were standing on a hypothetical platform at Saturn's orbit and looked up, you wouldn't see a bright point of light in the sky. You would see a vast, dull, red surface stretching across the entire sky, glowing like hot coals. You would be inside the star. Only Uranus at 19 astronomical units and Neptune at 30 astronomical units would orbit outside the star's surface. The Kuiper belt, that region of icy objects beyond Neptune, would remain safely in the darkness beyond this cosmic giant. Now, let's think about this in terms of volume. The volume of a sphere increases with the cube of its radius. If Stephenson 218's radius is about 2,000 times larger than the Sun's radius, its volume is 2,000 cubed. That is 2,000 times 2,000 times 2,000, about 10 billion. You could fit roughly 10 billion suns inside Stephenson 218, not 10, not 100, not 1 million, 10 billion. If our Sun were a tennis ball, Stephenson 218 would be a sphere roughly 1,000 feet across, about the height of a 100-story skyscraper. If our Sun were a marble, Stephenson 218 would be larger than a typical house. The scale is genuinely difficult for human brains to process. But here's where it gets even stranger. Despite being 10 billion times larger in volume, Stephenson 218 only contains about 12 to 16 times more mass than our Sun. How is that possible? The answer is density. Stephenson 218 is part of a massive star cluster called Stephenson 2, discovered in 1990 by astronomer Charles Bruce Stephenson. The cluster sits in the galactic plane, embedded in dense regions of dust and gas. This location makes it very difficult to observe because the dust absorbs and scatters light, especially visible light. Early observations of the cluster were done using infrared telescopes, which can penetrate dust better than visible light telescopes. Infrared observations revealed that Stephenson 2 contains some of the most massive and most luminous stars known. Among these giants, one star stood out. Stephenson 218 showed characteristics suggesting it was extraordinarily large, even compared to other hypergiants in the cluster. Measuring the size of a star this distant requires indirect methods. You can't simply point a telescope at it and measure its diameter the way you might measure the moon's. At 19,000 light-years away, even the largest stars appear as nothing more than points of light. Instead, astronomers use a combination of techniques. First, they measure the star's brightness, its apparent magnitude, which tells us how bright it appears from Earth. Then they estimate its distance using various methods, often by studying the entire cluster it belongs to. From brightness and distance, you can calculate luminosity, the total amount of energy the star emits per second. Stephenson 218 has a luminosity roughly 440,000 times greater than our Sun. That means every second it is pumping out 440,000 times more energy than our Sun does. Next, astronomers measure the star's temperature by analyzing its spectrum, the way its light spreads out into different colors. Different temperatures produce different spectral signatures. Stephenson 218 has a surface temperature of approximately 3,600 Kelvin, which translates to about 6,000 degrees Fahrenheit. That might sound hot, and it is, but it's actually cool for a star. Our Sun's surface temperature is about 5,770 Kelvin, or 10,000 degrees Fahrenheit. So, Stephenson 218 is cooler than our Sun, which is why it glows red rather than yellow-white. Cool stars appear red, hotter stars appear blue or white. Once you know luminosity and temperature, you can calculate radius using a relationship called the Stefan-Boltzmann law. This law relates a star's luminosity to its temperature and surface area. A cool star with enormous luminosity must have an enormous surface area to emit that much energy. The calculations for Stephenson 218 yield a radius somewhere between 2,000 and 2,400 times the Sun's radius. The uncertainty exists because measuring the star's exact temperature and luminosity at such a distance introduces margins of error. But even at the conservative end of estimates, this star is mind-bendingly large. 2,000 solar radii translates to about 930 million miles in radius, or about 1,860,000,000 miles in diameter. At the upper end of estimates, 2,400 solar radii, the radius reaches roughly 1,120,000,000 miles, with a diameter of about 2,240,000,000 miles. Either way, it is the largest star we have ever found. There are other contenders. Stars like UY Scuti, VV Cephei A, and WOHG 64 have all been proposed as candidates for the largest known star at various times. Measurements keep getting refined as better instruments come online and better data becomes available. For a while, UY Scuti held the record with radius estimates around 1,700 solar radii. But updated measurements using more precise data have brought that number down to around 755 solar radii, making it smaller than originally thought. Stephenson 218, based on current best estimates, appears to be larger. But astronomy is a science of continuous refinement. Future observations with better instruments might change these numbers. What we can say with confidence is that Stephenson 218 is among the largest stars ever discovered, and very likely the largest. Now, here's a question. Why are there limits on how large a star can become? You might think that with enough mass, you could just keep building a bigger and bigger star. But stellar physics doesn't work that way. There are hard limits imposed by the fundamental forces of nature. Stars shine because of nuclear fusion in their cores, Hydrogen atoms fuse together to form helium, releasing energy in the process. This energy creates outward pressure, pushing against the inward pull of gravity. A star is in a constant battle between these two forces. Gravity tries to compress the star. Fusion pressure tries to expand it. When the two forces balance, the star is stable. But very massive stars, those with more than about 8 to 10 times the Sun's mass, live fast and die young. They burn through their fuel at prodigious rates. The more massive a star is, the hotter and denser its core must be to generate enough pressure to hold itself up against gravity. This higher core temperature means fusion happens faster. Massive stars burn through their hydrogen in just millions of years instead of billions. When they run out of hydrogen in the core, they start fusing helium into carbon. When helium runs out, they fuse carbon into heavier elements. This process continues up the periodic table, creating oxygen, neon, magnesium, silicon, and eventually iron. Each stage produces less energy than the previous stage and happens faster. A massive star might spend millions of years fusing hydrogen, thousands of years fusing helium, hundreds of years fusing carbon, and just days fusing silicon into iron. Iron is where the process stops. Fusing iron doesn't release energy, it consumes energy. Once a massive star builds up an iron core, fusion shuts down. The outward pressure vanishes. Gravity wins. The core collapses in a fraction of a second, triggering a supernova explosion. Now, here's the key point for understanding size limits. As a star evolves off the main sequence and starts fusing heavier elements, it expands. The core contracts and heats up, but the outer layers expand and cool. This is why old massive stars become red supergiants, or, in extreme cases, hypergiants. Stephenson 218 is a hypergiant. It is in a late stage of stellar evolution, approaching the end of its life. It has swollen to an enormous size because its core is contracting while its envelope expands. But there's a limit to how large this expansion can go. The limit comes from something called the Eddington limit. This is the point where the outward pressure from radiation becomes so strong that it overcomes gravity and starts blowing the star apart. Stars emit light, and light carries momentum. When photons stream outward from a star, they push on the atoms in the star's outer layers. In normal stars, this radiation pressure is negligible compared to gravity. But in extremely luminous stars, radiation pressure becomes significant. In hypergiants like Stephenson 218, radiation pressure is enormous. The star is emitting 440,000 times more light than our Sun. All those photons streaming outward are pushing on the star's outer layers. If the star got any brighter for its mass, the radiation pressure would exceed gravity. The outer layers would be blown away into space. This is exactly what happens in the most massive stars. They shed mass through powerful stellar winds, losing material continuously. Stephenson 218 is almost certainly losing mass this way. Its outer envelope is likely being gradually stripped away by its own radiation. Eventually, the star will lose so much mass that it can no longer maintain its enormous size. It will collapse, trigger a supernova, and likely leave behind either a neutron star or a black hole. So, the size limit for stars isn't really about how much mass you can pile up. It's about the balance between gravity, radiation pressure, and the star's evolutionary state. Stephenson 218 sits near that limit. Any larger, and it would likely blow itself apart. Let's talk about what it would be like to visit this star, hypothetically. Imagine you're in a spacecraft approaching Stephenson 218 from a distance of several astronomical units. The star would dominate your entire field of view. It wouldn't look like a point of light anymore. It would look like a vast glowing wall filling the sky. As you got closer, the star's reddish color would become more apparent. This is a cool star by stellar standards, glowing red-orange rather than white or blue. The surface would be dim compared to our Sun. Despite being 440,000 times more luminous overall, the light is spread out over such an enormous surface area that the surface brightness is actually quite low. If you could somehow stand on a platform at the star's surface and look around, the local area wouldn't be blindingly bright. It would glow dully, like hot coals in a fireplace. You could possibly look directly at the surface without your eyes being instantly destroyed, though the infrared radiation would still kill you quickly. The real danger wouldn't be visible light, it would be heat. Even though the surface temperature is only about 3,600 Kelvin, the sheer amount of radiation being emitted would cook anything nearby. At the distance of Earth's orbit from the center of this star, assuming you could somehow survive inside the star's outer envelope, the temperature would be several thousand degrees. Everything would be plasma. No solid matter could exist. As you approached the core, temperatures would climb into the millions of degrees. The core of Stephenson 218, where fusion is taking place, likely reaches temperatures of several hundred million degrees Kelvin. At those temperatures, matter breaks down into bare nuclei and free electrons. The pressure is millions of times greater than Earth's atmospheric pressure. Nothing remotely like a physical structure could exist there. It is a realm of pure energy and fundamental particles. Now, one of the most remarkable things about Stephenson 218 is just how temporary its existence is. Stars like this are rare, not just in space, but in time. Our Sun has a total lifespan of about 10 billion years. It is currently about 4.6 billion years old, roughly halfway through its life. It will continue fusing hydrogen for another 5 billion years or so before it runs out of fuel and swells into a red giant. Stephenson 218, by contrast, will live for maybe 20 million years total, maybe less. It might have already exploded as a supernova, and we just don't know it yet because the light from that explosion is still traveling toward us. Remember, the star is 19,000 light-years away. What we see today is what the star looked like 19,000 years ago. If it exploded 10,000 years ago, we wouldn't know for another 9,000 years. This time-scale asymmetry is one of the strange consequences of looking at objects light-years away. You are always looking into the past. When Stephenson 218 finally does explode, and it will, the explosion will be spectacular. Hypergiants like this are thought to end their lives in supernovae, possibly even hypernovae, which are supernovae on steroids. A hypernova releases more energy than a typical supernova, possibly enough to create a gamma-ray burst. Gamma-ray bursts are the most energetic events in the universe, aside from the Big Bang. They release more energy in a few seconds than our Sun will emit in its entire 10 billion year lifetime. If Stephenson 218 produces a gamma-ray burst when it dies, and if that burst is aimed in our direction, it could be visible from Earth even at 19,000 light-years away. It would appear as an incredibly bright point of light in the constellation Scutum, potentially visible during the day for a short period. But we don't need to worry about danger. At 19,000 light-years, the radiation would be dispersed and absorbed by interstellar material long before reaching Earth. We would be safe. We would just get a spectacular light show. The supernova remnant would expand outward at a significant fraction of the speed of light, plowing into surrounding gas and creating a glowing nebula. That nebula would remain visible for thousands of years, slowly fading as it cooled and dispersed. The core would collapse. Given the star's estimated mass, somewhere between 12 and 16 solar masses, it is right on the borderline between forming a neutron star or a black hole. Neutron stars form from stars with cores between about 1.4 and 3 solar masses. Above that, the core collapses all the way down into a black hole. Stephenson 218's fate depends on how much mass it has lost through stellar winds. If it has shed enough mass, the remaining core might form a neutron star. If it has retained most of its mass, it could form a black hole. Either way, the hypergiant will be gone, replaced by a compact remnant. Let's put Stephenson 218 into context with other extreme stars to give you a sense of just how unusual it is. Our Sun is a G-type main sequence star, fairly average in size and mass. Most stars in the galaxy are actually smaller and cooler than the Sun. Red dwarfs, the smallest stars that can sustain fusion, make up about 70% of all stars. A typical red dwarf might have a radius of only 10 to 20% of the Sun's radius, and mass perhaps 10 to 50% of the Sun's mass. Red dwarfs are tiny, dim, and incredibly long-lived. The smallest red dwarfs will burn for trillions of years. At the other extreme, you have blue supergiants and hypergiants. These are massive, hot, and incredibly luminous. Rigel, the bright blue star in Orion's foot, is a blue supergiant with a radius about 79 times the Sun's radius. It is enormous compared to the Sun, but minuscule compared to Stephenson 218. Then there are red supergiants, cooler stars that have swollen to enormous sizes. Betelgeuse, the red star in Orion's shoulder, is perhaps the most famous red supergiant. Its radius varies because the star pulsates, but estimates put it somewhere around 764 solar radii. That's huge. If you placed Betelgeuse where the Sun is, its surface would extend past the orbit of Mars, possibly reaching the asteroid belt. But Stephenson 218 is still nearly 3 times larger. Antares, another famous red supergiant in the constellation Scorpius, has a radius of about 680 solar radii. Now there's an important caveat to mention. Measuring stellar radii, especially for distant red hypergiants, is extraordinarily difficult. These stars are often surrounded by thick clouds of dust ejected from their own surfaces. The dust absorbs and scatters light, making it hard to determine where the star's surface actually is. Additionally, many of these stars pulsate, expanding and contracting over months or years. Their size isn't constant. Stephenson 218 might be larger at some times and smaller at others. The measurements we have are snapshots, and they come with error bars. The radius estimate of 2,000 to 2,400 solar radii is a range, not a precise number. Future observations with better instruments might refine this. It is possible that another star could be found to be larger. It is possible that improved measurements could show Stephenson 218 is smaller than currently thought. But based on the best data available right now, it is the largest. Let's talk about the cluster this star calls home. Stephenson 2 is an open cluster, a group of stars that form together from the same molecular cloud. The cluster is young by stellar standards, only about 20 million years old. It contains some of the most massive stars in the galaxy, including multiple red supergiants and hypergiants. The cluster's location in the galactic plane means it is embedded in dense star-forming regions. There is active star formation happening nearby. This environment is rich in gas and dust, the raw materials for making stars. Stephenson 2 is thought to be one of the most massive young clusters in the Milky Way. It contains an estimated 50,000 to 100,000 solar masses worth of stars. Some of the other notable members include Stephenson 2-3, another red hypergiant, and Stephenson 2-7, also a red supergiant. These are all massive stars in late stages of evolution. Within a few million years, many of them will explode as supernovae. The cluster will eventually be torn apart by these explosions and by gravitational interactions. Young clusters like Stephenson 2 don't last long. Over tens of millions of years, the stars drift apart, dispersing into the general galactic population. So the cluster we see today is a temporary association. It is a snapshot of a brief moment in the galaxy's history when a bunch of massive stars happened to be in the same place. In 100 million years, Stephenson 2 as a cluster won't exist anymore. Its stars will be scattered across a large region of the galaxy. But the legacy of these stars will remain. When they explode, they'll enrich the interstellar medium with heavy elements: carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements created in their cores and during their supernova explosions. These elements will become part of new clouds of gas and dust. Those clouds will collapse to form new stars and planets. The atoms in your body, the iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created in stars. Most of it was created in stars like Stephenson 2-18. Massive stars are the universe's element factories. They are where the complexity of chemistry is built. Without massive stars, the universe would consist only of hydrogen and helium. No rocky planets, no water, no life. Stars like Stephenson 2-18 are rare, but they are crucial to the universe's ability to create complexity. They live fast, die young, and in their death throes, they seed the cosmos with the building blocks of future worlds. Now, let's address a common question. Could life exist on a planet orbiting a star like Stephenson 2-18? The short answer is no, not in any way we would recognize. First, the star's lifetime is far too short. Life as we know it took billions of years to develop on Earth. Simple single-celled organisms appeared about 3.8 billion years ago. Complex multicellular life didn't appear until about 600 million years ago. Intelligent life is even more recent. A star like Stephenson 2-18 will only live for about 20 million years total. That is not remotely enough time for life to evolve from chemistry. Second, the star's environment is incredibly hostile. Even if a planet somehow formed in orbit around this star before it became a hypergiant, which is unlikely, the planet would be subjected to intense radiation. The star's luminosity varies as it pulsates. The stellar wind would be stripping away any atmosphere. When the star swelled into a hypergiant, it would have engulfed any planets that were in close orbits. Planets that started out in the habitable zone would have been vaporized as the star expanded. Third, massive stars like this emit a lot of ultraviolet radiation and X-rays. This high-energy radiation would break apart molecules, making it extremely difficult for complex chemistry to survive on any nearby planet. The only way a planet could possibly be habitable around a star like this would be if it orbited very far away, many astronomical units out, well beyond the star's swollen envelope. But even then, the star's lifetime would be too short and the radiation environment too harsh. So no, planets around hypergiants are not good places to look for life. Life, as far as we understand it, needs stable conditions over long timescales. It needs a star that will shine steadily for billions of years, providing consistent energy. It needs liquid water, organic molecules, and protection from radiation. Hypergiants provide none of these things. They are spectacular objects crucial to the chemical evolution of the universe, but not homes for life. The best places to look for life are around stars like the Sun, medium-mass stars that burn steadily for billions of years, providing stable energy output over geological timescales, or possibly around red dwarfs, the smallest stars which burn for trillions of years, though they have their own challenges with flares and tidal locking. Hypergiants are fascinating, but they are factories, not nurseries. They make the elements needed for life, but they don't host it. Here's another angle to consider. What if you could harness the energy of a star like Stephenson 218? The concept of a Dyson sphere, a megastructure that surrounds a star to capture all its energy, was proposed by physicist Freeman Dyson in 1960. The idea is that an advanced civilization could build a swarm of solar collectors orbiting a star, capturing a significant fraction of its energy output. For a star like the Sun, this would provide enormous energy, far more than humanity currently uses. For a star like Stephenson 218, the energy available would be staggering. Remember, this star outputs 440,000 times more energy than the Sun. If you could capture even a small fraction of that energy, you would have power on a scale almost beyond comprehension. But building a Dyson sphere around Stephenson 218 would be impractical for several reasons. First, the star's lifespan is too short. By the time you built the megastructure, the star would be nearing the end of its life. You would invest enormous resources into a project that would only last a few million years at most before the star exploded and destroyed everything. Second, the star is so large that the amount of material needed to build a structure around it would be prohibitive. To build a solid shell around a star with a radius of 2 billion miles would require more material than exists in the entire solar system. You would need to dismantle thousands of planetary systems to gather enough raw materials. Third, the star's intense radiation and violent stellar winds would make construction and maintenance nearly impossible. Any structure would be subjected to constant bombardment of high-energy particles and radiation. It would need to be incredibly robust, far beyond anything we can currently imagine building. A more practical approach would be to build your Dyson sphere around a stable, long-lived star, a star like the Sun, or even a red dwarf. Stars that will shine steadily for billions of years, providing reliable energy for a civilization's entire history. Stephenson 218 is impressive, but it is not a good candidate for long-term energy harvesting. It is too unstable, too short-lived, and too violent. Now let's zoom out and think about the role of stars like Stephenson 218 in the galaxy's evolution. The Milky Way has been forming stars for over 13 billion years. During that time, countless generations of stars have been born, lived, and died. The first stars, called Population 3 stars, formed from pure hydrogen and helium. No heavy elements existed yet, because heavy elements are only created in stars. These first stars were likely very massive, burning hot and fast, exploding as supernovae after just a few million years. Their explosions seeded the universe with the first heavy elements: carbon, oxygen, nitrogen, silicon, magnesium, iron. These elements mixed with the remaining hydrogen and helium, creating chemically enriched gas clouds. The next generation of stars, Population 2 stars, formed from this slightly enriched material. They contained a small fraction of heavy elements, enough to allow more complex chemistry in any surrounding material. Our Sun is a population 1 star, part of the most recent generation. It formed about 4.6 billion years ago from gas that had already been enriched by multiple previous generations of stars. The solar system's planets, including Earth, formed from material that contained about 2% heavy elements by mass. That 2% came entirely from previous stars. Stars like Stephenson 218 are part of this ongoing cycle. When it explodes, it will scatter heavy elements into the interstellar medium. Those elements will eventually become part of new stars and planets. This is how the galaxy gradually becomes more metal-rich over time. Astronomers call any element heavier than helium a metal, even though most of them aren't metals in the chemistry sense. When they say a star is metal-rich, they mean it contains a higher fraction of elements heavier than helium. Metal-rich stars are younger. They formed from gas that had been processed through multiple earlier generations of stars. Metal-poor stars are older. They formed from gas that had been less enriched. Stephenson 218 is a young, metal-rich star. It formed from gas that already contained significant amounts of heavy elements from previous stellar generations. And when it dies, it will add even more heavy elements to the mix, contributing to the galaxy's ongoing chemical evolution. This process is why the universe is able to create complex structures. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. Everything else, every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in Earth's core, all of it was made in stars. Most of it was made in massive stars like Stephenson 218. These stars are the universe's alchemists. They take simple elements and forge them into complex ones. They live briefly but brilliantly, and in their death they enrich the cosmos. Without them, the universe would be a far simpler, far less interesting place. Let's think about observation. How do we actually study a star like Stephenson 218? It's not like we can send a probe there. At 19,000 light-years away, even traveling at the speed of light, it would take 19,000 years to reach it. No spacecraft we have built could make that journey. Voyager 1, our fastest and most distant probe, has been traveling for over 47 years and has only covered about 0.002 light-years. At that rate, it would take millions of years to reach Stephenson 218. So, we study it from a distance using telescopes. We collect light from the star, split that light into a spectrum, and analyze the patterns. Different elements absorb and emit light at specific wavelengths. By studying which wavelengths are present or absent, we can determine the star's composition, temperature, velocity, and other properties. We can also measure the star's brightness over time to see if it varies. Many red hypergiants are variable stars, meaning their brightness changes periodically. This variation is caused by pulsations. The star expands and contracts, changing its size and temperature, and therefore its brightness. By tracking these variations, we can learn about the star's structure and dynamics. Some observations are done in visible light, but many are done in infrared. Stephenson 218 is heavily obscured by dust, both in the cluster itself and in the interstellar medium between us and the star. Infrared light penetrates dust better than visible light, allowing us to see through the obscuration. Radio observations can also be useful. Stars emit radio waves, and studying those waves can reveal information about stellar winds, magnetic fields, and other phenomena. Interferometry, combining light from multiple telescopes to act as a single larger telescope, can achieve higher resolution. This technique has been used to directly measure the sizes of some nearby giant stars. For stars as distant as Stephenson 218, interferometry is challenging but potentially possible with large enough baselines. Most of what we know comes from photometry and spectroscopy. Photometry is measuring brightness. Spectroscopy is measuring the spectrum. Together, they give us a remarkably complete picture of a star's properties. We can determine its temperature, luminosity, composition, mass, radius, age, and evolutionary state, all from light collected across 19,000 light-years of space. It is a testament to human ingenuity and the power of physics that we can learn so much about an object we will never physically reach. Here's a thought. How many stars like Stephenson 218 exist in the galaxy? The answer is not many. Hypergiants are exceedingly rare. Out of the hundreds of billions of stars in the Milky Way, only a few dozen hypergiants have been identified. This rarity is partly because hypergiants are genuinely uncommon and partly because they are hard to find. They are often obscured by dust, located in distant or crowded regions, and they don't live long. Even if the galaxy produces a hypergiant every few thousand years, each one only lasts for a few million years. That means at any given time, there might only be a few thousand of them in existence across the entire galaxy. And most of those are too distant or too obscured for us to detect. The ones we have found are mostly nearby, within a few tens of thousands of light-years. Stephenson 218, at 19,000 light-years, is one of the more distant ones we have studied in detail. There are almost certainly other hypergiants farther away, hidden from us by distance and dust. We will probably discover more as our instruments improve and our surveys cover more of the sky. But hypergiants will always be rare. They represent a brief, extreme phase in the life of the most massive stars. Most stars never become hypergiants. They are not massive enough. Only stars with initial masses above roughly 20 to 25 solar masses can evolve into hypergiants. And even then, only under certain conditions. Most massive stars explode as supernovae while they are still blue supergiants. Only some evolve into red supergiants, and only a fraction of those become hypergiants. So Stephenson 218 is a rare object, a glimpse at the extreme end of stellar evolution, a star that has pushed the limits of size to the breaking point. Let's return to that visualization we started with. Imagine standing on Earth and looking up at the night sky. Now imagine that instead of the Sun, Stephenson 218 sits at the center of our solar system. The sky would be utterly transformed. During the day, you wouldn't see a bright point of light overhead. You would see a vast, dull red disk covering a huge portion of the sky. The star's surface would be close enough that it would appear as a disk, not a point. And because you would be inside the star's outer envelope, the sky would be filled with glowing gas. Of course, Earth wouldn't exist in this scenario. The planet would have been vaporized when the star expanded. But if somehow you could have a platform floating in space at the distance where Earth normally orbits, say 1 astronomical unit from the center, you would be deep inside the star's atmosphere. The temperature would be thousands of degrees. The pressure would be immense. You would be surrounded by glowing plasma. Looking outward, you would see a gradually brightening glow toward the star's core and a dimming glow toward the surface. There would be no sharp boundaries, no clear sense of up or down, just an endless sea of glowing gas in all directions. It is a vision of hell in some sense, a place utterly hostile to anything resembling life or structure. And yet it is also a place of creation. This is where heavy elements are being forged, where the raw materials for future planets and future life are being created. The same processes that make this environment lethal are the processes that make the universe capable of complexity. Fusion in the core, convection in the envelope, mass loss through stellar winds, eventually a supernova that will scatter enriched material across light years of space. These aren't just destructive processes, they are constructive. They are how the universe builds the chemical foundation for everything that comes after. Stephenson 218 will not last. Within a few million years, possibly within the next million years, it will explode. The explosion will be visible from Earth, a bright new star appearing in the constellation Scutum. It will outshine most of the stars in the night sky for weeks or months before gradually fading. The remnant will expand outward, eventually forming a nebula that might be visible for thousands of years. And then slowly the nebula will disperse. The elements created in the star and in the supernova will mix with the interstellar medium. New stars will form from that enriched material. Some of those stars will have planets. Some of those planets might develop life. And if they do, that life will owe its existence in part to Stephenson 218. The carbon in its molecules, the oxygen in its atmosphere, the iron in its core, all of it will have been created in stars like this one. This is the legacy of hypergiants. They don't leave behind stable systems or long-lived structures. They leave behind enriched material, the seeds of future complexity. Now, before we close, let's think about what Stephenson 218 means for our understanding of the universe. This star challenges our models of stellar evolution. Stars this large shouldn't be stable, yet they exist. They should blow themselves apart under their own radiation pressure, yet they hold together, at least for a while. Studying stars like this helps refine our theories. It shows us the extremes, the edge cases where our models are tested. Every observation of a hypergiant gives us more data, more constraints on the physics. And there's still a lot we don't understand. We don't fully understand the mass loss mechanisms. How exactly does a hypergiant shed mass through stellar winds? What drives those winds? How much mass is lost over the star's lifetime? We don't fully understand the internal structure. What is happening in the core? How does convection work in a star this large and this diffuse? Are there layers or shells of different compositions? We don't fully understand the end state. Will Stephenson 218 explode as a normal supernova? Or will it produce something more exotic? Could it collapse directly into a black hole without a visible explosion? These are open questions, and the only way to answer them is to keep observing, keep building better instruments, keep refining our models. Stephenson 218 is one data point in a larger effort to understand how stars work. But it is an important data point because it represents the extreme, and understanding the extremes helps us understand the full range of behavior. If we only studied stars like the Sun, we would have a very incomplete picture. We need to study the smallest stars, the largest stars, the hottest, the coolest, the youngest, the oldest. Every type of star teaches us something different. Hypergiants teach us about the limits. How large can a star become? How luminous? How unstable? What happens when you push the physics to the breaking point? Stephenson 218 is an answer to some of those questions and a source of new questions for others. Let me tell you more about what makes red hypergiants specifically so fascinating. These stars exist in a very narrow evolutionary phase. They are massive stars that have exhausted the hydrogen in their cores and moved on to fusing heavier elements. But they haven't yet reached the final stages that lead to supernova. They are in transition, and that transition creates unique conditions. The core of a red hypergiant is contracting and heating up as it fuses helium into carbon and oxygen. This contraction releases gravitational energy which heats the surrounding layers. Those outer layers respond by expanding dramatically. It is counterintuitive, but it is how stellar physics works. A contracting core leads to an expanding envelope. The envelope expands so much that it cools down significantly. The surface temperature drops from tens of thousands of degrees for a main sequence massive star to just a few thousand degrees for a red hypergiant. This cooling causes the star to glow red instead of blue or white. But despite the cooler surface, the total energy output actually increases. The star becomes more luminous because the surface area is so enormously larger. Think about it this way. A small hot piece of metal radiates a certain amount of energy. A huge warm piece of metal might radiate much more total energy even though each square inch is cooler. That is what is happening with red hypergiants. The surface is cooler per unit area, but there is so much more surface area that the total output is staggering. Now, one of the most interesting things about these stars is their instability. Red hypergiants are not stable objects. They pulsate. They vary in brightness. They shed mass erratically. The outer envelope is so loosely bound that it is constantly being lost to space. Powerful stellar winds carry away material at rates that would horrify any engineer trying to build a stable system. Some estimates suggest Stephenson 218 might be losing mass at a rate of about 1/10,000th of a solar mass per year. That might not sound like much, but over 1,000,000 years, that is 100 solar masses, more mass than many entire stars contain. This mass loss has profound consequences. It means the star is constantly getting smaller, losing its outer layers. It also means the space around the star is filled with previously ejected material. This creates a circumstellar envelope, a cloud of gas and dust surrounding the star. When we observe Stephenson 218, we are not just seeing the star itself. We are seeing the star plus this surrounding material. That makes precise measurements even more difficult because you have to account for the contribution from the circumstellar material. Some of that material is being pushed away by radiation pressure. Photons from the star hit dust grains and atoms in the envelope, transferring momentum. This pressure pushes material outward, creating a wind, but it is not a smooth, steady wind. It is clumpy, variable, and irregular. Observations show that red hypergiants can have large-scale convection cells on their surfaces. These are rising and falling currents of hot and cool gas, similar to the convection you see in boiling water, but on an unimaginably larger scale. A single convection cell might be larger than the entire orbit of Earth around the Sun. These convection cells create hot spots and cool spots on the star's surface. As the star rotates, which it does, albeit slowly, these spots move in and out of view. This causes variations in brightness that we can measure from Earth. By studying these variations, astronomers can learn about the star's rotation rate, its surface structure, and the physics of convection at extreme scales. Another source of variability comes from pulsations. The star expands and contracts over periods of months or years. During expansion, the surface moves outward, the star gets larger, and the temperature drops slightly. During contraction, the opposite happens. These pulsations are driven by the Kappa mechanism, a feedback loop where increased opacity in the star's outer layers causes them to absorb more radiation, heat up, expand, then cool and contract again. It is a natural oscillation like a spring bouncing up and down. For Stephenson 218, these pulsations might change the star's radius by 10 or 20% over the course of a year or two. That means the star could vary from about 1,800 solar radii to 2,200 solar radii over a pulsation cycle. Measuring these variations helps astronomers understand the star's internal structure, because the pulsation period depends on the star's mass, radius, and internal density distribution. Now let's think about the star's magnetic field. Most stars have magnetic fields generated by dynamo processes in their interiors. The Sun has a magnetic field that creates sunspots, flares, and coronal mass ejections. Red hypergiants likely have magnetic fields too, though they are much harder to measure because the stars are so distant. The magnetic field in a red hypergiant would be shaped by the star's rotation and convection. As convective cells rise and fall, they drag magnetic field lines with them, creating complex, tangled magnetic structures. These magnetic fields might play a role in driving mass loss. They could channel material away from the star along magnetic field lines, similar to how the Sun's magnetic field channels solar wind. They might also create hotspots where magnetic field lines concentrate energy, heating localized regions of the star's atmosphere. These hotspots could contribute to the X-ray emission that has been detected from some red hypergiants. X-rays from a cool star might seem contradictory, but magnetic activity can create small regions of extremely hot plasma even in an otherwise cool stellar atmosphere. The study of red hypergiant magnetic fields is an active area of research. Better instruments, particularly spectropolarimeters that can measure the polarization of light caused by magnetic fields, are helping astronomers map these fields. Each new observation adds to our understanding of how these extreme stars work. Let's talk about some specific comparisons to help you really grasp the scale we are dealing with. Stephenson 218's radius is approximately 930 million miles. Let's break that down into different units to see it from multiple angles. In astronomical units, it is about 10 astronomical units. Remember, 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. So this star's radius alone is 23 times the Earth-Sun distance. Its diameter, therefore, is about 20 astronomical units. Neptune, the outermost planet in our solar system, orbits at about 30 astronomical units from the Sun. If you place Stephenson 218 at the center of our solar system, its surface would extend well beyond Neptune's orbit. Pluto, the dwarf planet, orbits at an average distance of about 39 astronomical units. Even Pluto would be inside the star. The Kuiper belt, the region of icy objects beyond Neptune, starts at around 30 astronomical units and extends to about 50 astronomical units. The Kuiper belt would remain safely outside the star's surface. Only objects within about 10 astronomical units would be engulfed. Now, let's think about time. Light travels at roughly 186,000 miles per second. In 1 second, light can circle Earth's equator about 7.5 times. Light takes about 8 minutes and 20 seconds to travel from the Sun to Earth. How long would it take light to cross Stephenson 218's diameter? The diameter is about 1,860,000,000 miles. Light travels 186,000 miles per second. Divide 1,860,000,000 by 186,000 and you get approximately 10,000 seconds. That is about 2 hours and 47 minutes. Light would take about 2 hours and 47 minutes to travel from one side of Stephenson 218 to the other. Compare that to the Sun, where light takes only about 4.6 seconds to cross the diameter, or Earth, where light takes about 0.042 seconds to cross. This star is so large that light, the fastest thing in the universe, takes more than 2 hours to cross it. If you were somehow at the center of Stephenson 218 and you sent a light signal to the surface, it would take about 1 hour and 24 minutes to get there. By that time, conditions might have changed significantly in the star's dynamic outer layers. Another comparison involves mass. We have said Stephenson 218 contains about 12 to 16 times the Sun's mass. The Sun's mass is approximately 2 times 10 to the power of 30 kilograms. That is a 2 followed by 30 zeros. It is about 330,000 times the mass of Earth. So Stephenson 218 contains somewhere between 24 and 32 times 10 to the power of 30 kilograms. That is equivalent to somewhere between 4 million and 5,300,000 Earths. But remember, this mass is spread out over a volume 10 billion times larger than the Sun. The average density is therefore about 1 billion times lower than the Sun. The Sun has an average density of about 1.4 grams per cubic centimeter, slightly higher than water. Stephenson 218's average density is about 0.000014 grams per cubic centimeter. That is 14 millionths of a gram per cubic centimeter. For comparison, the best vacuum we can create in laboratories on Earth is about 1 trillionth of a gram per cubic centimeter. So even the star's average density is thousands of times higher than laboratory vacuum. But it is incredibly low by stellar standards. The core would be much denser, perhaps approaching or exceeding the Sun's core density. But the outer envelope is extraordinarily thin, almost nothing by any terrestrial standard. Now let's explore the historical context of red hypergiant discovery. For most of human history, stars were thought to be unchanging, eternal points of light. The ancient Greeks called them the fixed stars, to distinguish them from the wandering stars, the planets. It wasn't until the Renaissance that astronomers began to realize stars could change. In 1572, Tycho Brahe observed a new star that appeared in the constellation Cassiopeia. It was brighter than Venus at its peak and visible during the day. This was a supernova, though that term wouldn't be coined for centuries. In 1604, Johannes Kepler observed another supernova in Ophiuchus. These observations challenged the idea that the heavens were unchanging, but the nature of stars themselves remained mysterious. Were they other suns like ours? Were they different types of objects? How far away were they? These questions weren't answered until the 19th and 20th centuries. The development of spectroscopy in the mid-1800s allowed astronomers to analyze starlight in detail. By splitting light into its component colors, scientists could identify which elements were present in a star's atmosphere. Different elements absorb and emit light at specific wavelengths, creating distinctive patterns. This technique revealed that stars are made mostly of hydrogen and helium, the same elements found on Earth, but in different proportions. It also revealed that stars come in different temperatures. Hot stars are blue, cool stars are red. In the early 1900s, astronomers Ejnar Hertzsprung and Henry Norris Russell independently developed what is now called the Hertzsprung-Russell diagram. This is a graph that plots stars' luminosity versus temperature. When you plot thousands of stars on this diagram, patterns emerge. Most stars fall along a diagonal band called the main sequence, where our Sun sits, but some stars lie off the main sequence. These are giants and supergiants. stars that are much more luminous than main sequence stars of the same temperature. Red giants and red supergiants occupy the upper right corner of the diagram, high luminosity but cool temperature. As telescopes improved and surveys catalogued more stars, astronomers found that the red giant region extends to extraordinarily high luminosities. Some stars are so luminous they dwarf anything else in their vicinity. These ultra-luminous cool stars were eventually classified as hypergiants. The term hypergiant was coined to distinguish them from regular supergiants. They are not just bigger, they are in a completely different category of extremity. Early examples included stars like VV Cephei, discovered in the 1930s to be a red supergiant with an enormous radius. Mu Cephei, also called Herschel's garnet star because of its deep red color, was another early known red supergiant. VY Canis Majoris was long thought to be the largest star known, with radius estimates in the 1990s suggesting it might be up to 2,800 solar radii. Later measurements revised that estimate downward to about 1,420 solar radii. Still enormous, but not quite as large as originally thought. This pattern of revising estimates is common in astronomy. As instruments improve and techniques get better, measurements become more accurate. Early estimates often have large uncertainties, and sometimes the true value turns out to be different from initial estimates. UI Scuti was another contender for the largest star, discovered in the 1860s. It wasn't until modern infrared observations that its true size was appreciated. Initial estimates suggested radii as high as 1,900 solar radii. Current estimates are lower, around 755 solar radii. Stephenson 218 entered this competition relatively recently. The cluster was discovered in 1990, but detailed studies of individual stars within it came later. It wasn't until the 2000s and 2010s that high-resolution infrared observations allowed astronomers to measure the properties of stars within the cluster accurately. Stephenson 218 emerged as a strong candidate for the largest known star based on these observations. Its large radius, combined with relatively high confidence in the measurements, puts it at or near the top of the list. But the competition continues. Astronomy is an ongoing process. New stars are discovered, old measurements are refined, and the rankings change. What we can say is that Stephenson 218 is among the largest stars ever found, and quite possibly the largest. Future observations will continue to refine our understanding. Let's think about the technology that allows us to study stars like this. Observing Stephenson 218 requires specialized instruments. Optical telescopes struggle because the star is heavily obscured by dust. The cluster sits in the galactic plane, the disk of the Milky Way, where most of the galaxy's gas and dust is concentrated. Between us and Stephenson 2, there is a significant amount of intervening material. This material absorbs blue and green light preferentially, allowing red light to pass through more easily. This is why the night sky appears darker in some directions than others, why the Milky Way band shows dark lanes and bright patches. Those dark lanes are dust clouds blocking the light from stars behind them. To see through this dust, astronomers use infrared telescopes. Infrared light has longer wavelengths than visible light, and it is less affected by dust. Dust grains that block visible light are often transparent to infrared. Several major infrared observatories have studied Stephenson 218. The Infrared Astronomical Satellite, IAAS, launched in 1983, was one of the first space-based infrared telescopes. It surveyed the entire sky in infrared, detecting hundreds of thousands of infrared sources, including many cool, dusty stars. IAS data helped identify the Stephenson 2 cluster as a region of interest. The 2-micron all-sky survey, 2MASS, conducted in the late 1990s and early 2000s, mapped the entire sky in near-infrared wavelengths. 2MASS data provided more detailed positions and brightnesses for stars in the cluster, allowing astronomers to start picking out individual members. The Spitzer Space Telescope, launched in 2003, provided even better infrared images and spectra. Spitzer could observe at longer infrared wavelengths than previous missions, allowing it to see cooler dust and deeper into obscured regions. Spitzer observations helped characterize the dust around stars like Stephenson 218. The Herschel Space Observatory, which operated from 2009 to 2013, observed at even longer wavelengths in the far infrared and sub-millimeter range. Herschel could see the coldest dust and gas, mapping out the material surrounding stars. Ground-based infrared telescopes have also played a major role. The Very Large Telescope in Chile, operated by the European Southern Observatory, has multiple instruments capable of infrared observations. The VLT's large mirrors and excellent site location in the Atacama Desert, one of the driest places on Earth, make it ideal for infrared work. The Keck telescopes in Hawaii, two of the largest optical infrared telescopes in the world, have also observed stars in the Stephenson 2 cluster. These telescopes can use adaptive optic systems that compensate for atmospheric turbulence in real time to achieve sharper images. Adaptive optics works by using a deformable mirror that changes shape hundreds of times per second to correct for distortions caused by Earth's atmosphere. This allows ground-based telescopes to achieve image quality close to what space telescopes can achieve, at least at infrared wavelengths where atmospheric distortion is less severe. Spectroscopy is crucial for understanding these stars. By spreading the star's light into a spectrum and analyzing which wavelengths are present, astronomers can determine temperature, composition, velocity, and other properties. High-resolution spectrographs, instruments that produce very detailed spectra, can detect absorption lines from specific elements and molecules. These lines tell us what the star is made of. In the case of Stephenson 218, spectroscopy reveals the presence of molecules like titanium oxide and water vapor in the star's atmosphere. These molecules only exist at relatively cool temperatures, which confirms the star's status as a cool hypergiant. Spectroscopy can also measure the star's radial velocity, how fast it is moving toward or away from us. This is done by measuring the Doppler shift of spectral lines. If the star is moving toward us, its light is blue shifted. All the wavelengths are slightly shorter than they would be if the star were stationary. If it is moving away, the light is red shifted. Wavelengths are slightly longer. The amount of shift tells us the velocity. For Stephenson 218, radial velocity measurements help confirm it is a member of the Stephenson 2 cluster. All the stars in the cluster should have similar radial velocities because they are all moving together through space. Photometry, measuring brightness over time, reveals variability. Automated survey telescopes scan the sky repeatedly, building up light curves that show how a star's brightness changes. For variable stars like Stephenson 218, these light curves reveal the timescales and amplitudes of variation. Is the star pulsating regularly or irregularly? How much does the brightness change? These details constrain models of the star's structure and dynamics. Interferometry is a technique that combines light from multiple telescopes to achieve higher resolution than any single telescope could. By precisely measuring the phase of light waves arriving at different telescopes, astronomers can reconstruct images with resolution equivalent to a telescope as large as the distance between the individual telescopes. The Very Large Telescope Interferometer, VLTI, has been used to measure the angular diameters of some nearby red supergiants. These measurements, combined with distance estimates, give direct measurements of physical size. For very distant stars like Stephenson 218, interferometry is challenging because the angular size is so small. But future interferometer arrays with longer baselines might be able to resolve it directly. That would provide a direct measurement of the star's size, removing much of the uncertainty from current estimates. Now let's explore what happens after a red hypergiant explodes. The supernova will be a Type II supernova, the type that occurs when a massive star's core collapses. Here's how it works. The star has been fusing progressively heavier elements in its core: hydrogen to helium, helium to carbon and oxygen, carbon to neon and magnesium, and so on. Each stage releases less energy and happens faster than the previous stage. Eventually, the core is fusing silicon into iron. This final stage lasts only a few days. Iron is the most stable nucleus. Fusing iron into heavier elements doesn't release energy, it consumes energy. So when the core becomes pure iron, fusion stops. The core is supported against gravity only by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too close together. But there's a limit to how much mass electron degeneracy pressure can support, called the Chandrasekhar limit for an iron core. That limit is about 1.4 solar masses. Once the core exceeds that mass, electron degeneracy pressure can't hold it up anymore. The core collapses, and it collapses fast. In less than a second, a core the size of Earth collapses to a sphere about 20 miles across. The density increases to nuclear density about 100 trillion times the density of water. Electrons are forced to combine with protons, forming neutrons and releasing neutrinos. The core becomes a neutron star, an object so dense that a teaspoon of it would weigh 1 billion tons. The collapse is so sudden that the outer layers of the star don't have time to react. They are still falling inward when the core reaches nuclear density and stops collapsing. The infalling material crashes into the now solid core and bounces back. This rebound creates a shock wave that propagates outward through the star. The shock wave is enormously energetic. It heats the outer layers to billions of degrees, high enough to trigger explosive nuclear synthesis. Elements heavier than iron, which can't be made by normal fusion, are created in the supernova explosion itself. Gold, platinum, uranium, and other heavy elements are made in this brief moment of extreme conditions. The shock wave blows the outer layers of the star into space at speeds of 10,000 to 30,000 miles per second. This ejected material forms an expanding shell called a supernova remnant. The remnant glows brightly as the shock wave heats the surrounding gas. From Earth, the supernova would appear as a new bright star in the constellation Scutum. It would suddenly appear where no bright star was before, possibly reaching magnitude -7 or -8. That is brighter than Venus, bright enough to be visible during the day. It would remain bright for weeks, then gradually fade over months. The light curve, the graph of brightness over time, would show an initial rapid rise as the shock wave reaches the surface, a peak as the maximum amount of material is heated, then a gradual decline as the expanding remnant cools and becomes transparent. The decline would be powered by the decay of radioactive isotopes created in the explosion, particularly nickel-56, which decays to cobalt-56 and then to iron-56. This radioactive decay provides energy that keeps the remnant glowing for months after the initial explosion. The neutrinos, released during core collapse, carry away most of the explosion's energy, about 99% of it. These neutrinos barely interact with matter and escape almost immediately, streaming out from the core at nearly the speed of light. Only about 1% of the energy goes into the visible explosion, but that 1% is still staggering. A typical Type II supernova releases about 10 to the 46 joules of energy in the form of kinetic energy and light. That is about 100 times the energy the Sun will emit in its entire 10 billion-year lifetime, released in a few seconds. The explosion would scatter about 10 to 15 solar masses of material into space. This material, enriched with heavy elements created in the star and in the supernova itself, would mix with the interstellar medium. Over millions of years, it would cool and condense, eventually becoming part of new clouds of gas and dust. Those clouds might collapse to form new stars. And those stars would be slightly more metal-rich than Stephenson 218. Continuing the process of chemical enrichment that has been happening since the first stars formed. The core remnant, the neutron star or black hole, would remain behind. If it is a neutron star, it might be detectable as a pulsar, a rapidly rotating neutron star that emits beams of radiation. As the neutron star rotates, these beams sweep across space like lighthouse beams. If one beam happens to point toward Earth, we detect regular pulses of radio waves, hence the name pulsar. Pulsars rotate incredibly fast, some spinning hundreds of times per second. They are incredibly dense, with magnetic fields trillions of times stronger than Earth's. They are some of the most extreme objects in the universe, and studying them teaches us about physics under conditions we can never recreate in laboratories. If the core is too massive for neutron degeneracy pressure to support, it collapses further into a black hole. A stellar mass black hole from a star like Stephenson 218 would have a mass of perhaps 10 to 15 solar masses. Its event horizon would be only about 60 to 90 miles across, tiny compared to the original star, but containing all the mass of the core. Black holes from stellar collapse are often found in binary systems, orbiting another star. If the companion star is close enough, the black hole can pull material off it, forming an accretion disk. Material in the accretion disk spirals inward, heating up to millions of degrees and emitting X-rays. These X-ray binary systems are some of the brightest X-ray sources in the galaxy. They are easier to detect than isolated black holes because the accreting material glows brightly. Isolated black holes, by definition, don't emit light, so they are very hard to find unless they happen to pass in front of a background star and gravitationally lens the starlight. The supernova remnant would expand outward at thousands of miles per second. Over thousands of years, it would grow to dozens of light years across. Eventually, it would fade as the material dispersed and cooled. Some famous supernova remnants include the Crab Nebula, the remnant of a supernova observed in 1054 AD. The Crab Nebula is powered by a pulsar at its center, which is spinning 30 times per second and pumping energy into the surrounding nebula. Cassiopeia A is another famous remnant from a supernova that occurred around 1680, though it wasn't observed at the time because it was heavily obscured by dust. These remnants are laboratories for studying supernova physics, shock waves, and the interaction between ejected material and the interstellar medium. Stephenson 218's remnant will one day join this list. It will become another expanding shell of enriched gas, glowing in radio and X-rays, slowly mixing with the galaxy's interstellar medium. One more thing worth discussing is the role of dust around these stars. Red hypergiants are surrounded by thick clouds of dust that they have ejected over millions of years. This dust forms when material in the star's outer envelope cools enough for molecules to condense into solid grains. In the hot inner regions close to the star, temperatures are too high for dust to exist. Gas is ionized, atoms are broken apart, but as you move outward, temperatures drop. At a few thousand degrees, molecules can form: water, carbon monoxide, titanium oxide, and others. As you move even farther out, temperatures drop below a few thousand degrees. At these temperatures, solid grains can condense from the gas: silicate grains, carbon grains, iron grains, depending on the composition of the gas and the local temperature and pressure. These grains are tiny, typically a fraction of a micron across, much smaller than a grain of sand, but collectively they form thick clouds that can completely obscure the star at visible wavelengths. The dust absorbs visible and ultraviolet light from the star, heats up and re-emits that energy as infrared radiation. This is why dusty stars are bright in the infrared. Even if they are faint in visible light, the energy is still there. It is just shifted to longer wavelengths. Radiation pressure from the star pushes the dust grains outward. Photons from the star hit the dust grains and transfer momentum, creating an outward force. For small grains, this force can overcome gravity, pushing them away from the star. As the dust grains move outward, they drag gas with them through collisions. This creates a dusty wind, a flow of gas and dust away from the star. The wind carries away mass, gradually stripping the star's outer layers. Over time, the star loses a significant fraction of its mass this way. For Stephenson 218, the circumstellar dust shell extends for many stellar radii. It might extend for tens or even hundreds of astronomical units from the star. This dust is what makes the star appear extremely bright in infrared surveys. Instruments like Spitzer and Herschel detected enormous amounts of cool dust around the star, far more than you would expect from a star without significant mass loss. This dust shell is evidence of the star's ongoing mass loss and its approaching end. The more dust there is, the more mass the star has lost, and the closer it probably is to supernova. When the supernova occurs, the shock wave will plow into this circumstellar material. The collision will heat the material to extremely high temperatures, causing it to glow brightly in X-rays and visible light. This interaction between the supernova ejector and the circumstellar material can last for years or decades after the explosion. It creates a bright, expanding shell that is easier to observe than the supernova remnant itself in later stages. Some supernovae show evidence of this interaction in their light curves. The light curve has an initial peak from the explosion itself, then a later bump or plateau as the ejector collide with circumstellar material. By studying these features, astronomers can learn about the mass loss history of the progenitor star, how much mass it lost and when. Let's also think about the ultimate fate of matter from Stephenson 218. Right now, the star contains 12 to 16 solar masses of material. Most of that material is hydrogen and helium, the most common elements in the universe. But there's also a significant amount of heavier elements: carbon, nitrogen, oxygen, and others. These heavy elements were created in earlier generations of stars and were part of the gas cloud that Stephenson 218 formed from. During the star's lifetime, fusion in the core has been creating even more heavy elements. Helium to carbon, carbon to oxygen, oxygen to silicon, silicon to iron. The core contains layers of different composition, like an onion. An iron core surrounded by a silicon shell, surrounded by an oxygen shell, and so on outward. When the supernova occurs, the explosion will create even more heavy elements through explosive nucleosynthesis. Elements heavier than iron, which can't be made by normal fusion, are created in the brief moment of the supernova. All of this enriched material, roughly 10 to 15 solar masses of it, will be scattered into space. It will mix with the interstellar medium, becoming part of the galaxy's reservoir of gas and dust. That gas and dust will eventually collapse to form new stars. Some of those stars will have rocky planets, planets made of elements created in stars like Stephenson 218. And if any of those planets develop life, that life will be made of atoms that once were part of Stephenson 218. This is the cosmic cycle of matter. Stars create heavy elements, scatter them into space, and new stars and planets form from the enriched material. Over billions of years, the galaxy becomes more and more metal-rich. Each generation of stars is slightly more enriched than the previous generation. Earth and the Sun formed about 4.6 billion years ago from a cloud that was already enriched with heavy elements from previous generations of stars. The iron in Earth's core, the oxygen in our atmosphere, the carbon in our bodies, all of it came from stars that lived and died before the Sun was born. And billions of years from now, after the Sun dies and scatters its outer layers into space, those atoms might become part of future stars and planets, maybe even future life. Matter is recycled endlessly through the cosmos. Stephenson 218 is part of that cycle, a brief, brilliant phase in the ongoing story of matter's journey through the universe. Before we close, I want to emphasize just how remarkable it is that we can study objects like this at all. Stephenson 218 is 19,000 light-years away. That is an almost incomprehensibly vast distance. If you traveled at the speed of a commercial airliner, about 600 miles per hour, it would take about 21 billion years to get there. That is longer than the current age of the universe. If you traveled at the speed of the Voyager spacecraft, about 38,000 miles per hour, it would still take about 340 million years. We can never physically visit this star. No spacecraft we can currently imagine could make the journey within a human lifetime, or even within human civilization's lifetime. And yet, we can study it in detail. We can measure its size, its temperature, its luminosity, its composition. We can watch it change over time, track its variability, map its structure. We can predict when it will explode and what will happen when it does. All from light that has traveled 19,000 years to reach us. Photons that left the star when humans were still living in small bands, hunting and gathering with no written language, no agriculture, no cities. Those photons have been traveling through space all this time, crossing the galaxy, threading through clouds of gas and dust, finally reaching Earth and entering our telescopes. And from those photons, we can reconstruct the entire life story of a star 2 billion miles across. That's the power of astronomy. That's the power of science. We take tiny clues, faint signals, subtle patterns in light, and from them we build a picture of the universe. We figure out how stars work, how they are born, how they live, how they die. We figure out the laws of physics that govern everything from the smallest atom to the largest galaxy. And we do it all from a small planet orbiting an average star in an unremarkable galaxy. It is one of humanity's greatest achievements, not building monuments or conquering territories, but understanding. Understanding how the universe works, understanding our place in it, understanding where we came from and where we are going. Stephenson 218 is a testament to that understanding. A star we will never touch, but we can study. A star we will never visit, but we can know. A star that exists in a realm of extremes we can barely imagine, and yet we can measure, analyze, and comprehend. Now, let's think about some of the practical challenges astronomers face when observing stars like Stephenson 218. One major challenge is atmospheric interference. Earth's atmosphere is constantly in motion, with currents of air at different temperatures creating turbulence. This turbulence causes stars to twinkle, which looks pretty to the naked eye, but is a nightmare for astronomers trying to make precise measurements. The twinkling is caused by light from the star being bent slightly as it passes through pockets of air with different densities. The image dances around, blurs and shimmers. For point sources like distant stars, this creates the twinkling effect. For extended objects like planets or nearby stars that appear as small disks, it creates blur. Adaptive optic systems can compensate for this to some degree. They work by measuring the distortions in real time using a guide star, either a real bright star near the target or an artificial star created by shining a laser into the upper atmosphere. The laser excites sodium atoms about 90 miles up, creating a glowing spot that acts as an artificial star. By measuring how the guide star's light is distorted, the adaptive optic system can figure out what the atmosphere is doing at that moment. It then adjusts a deformable mirror in the telescope, changing its shape hundreds or thousands of times per second to cancel out the atmospheric distortions. This dramatically improves image quality, allowing ground-based telescopes to achieve resolution close to their theoretical limit. But adaptive optics only works well at infrared wavelengths. At visible wavelengths, atmospheric turbulence changes too quickly for the system to keep up perfectly. So even with adaptive optics, ground-based observations have limitations. Space-based telescopes don't have this problem because they are above the atmosphere. The Hubble Space Telescope, for instance, can observe at visible wavelengths with no atmospheric interference. But Hubble is optimized for visible and ultraviolet light, not infrared. For infrared observations, you need specialized instruments. The James Webb Space Telescope, launched in December 2021, is a powerful infrared observatory. It has a much larger mirror than Hubble and is optimized for infrared wavelengths. Webb can observe very faint, very cool objects that are invisible to Hubble. It is likely that Webb will eventually observe Stephenson 218 and other red hypergiants in unprecedented detail. Its high-resolution infrared imaging might allow direct measurement of the star's angular size, which combined with distance estimates would give a precise physical radius. Webb's spectrographs could analyze the star's atmospheric composition in detail, identifying specific molecules and isotopes. This would provide clues about the star's evolutionary history and internal processes. Another challenge is distance measurement. Knowing how far away a star is crucial for determining its physical properties. Brightness alone doesn't tell you much because a faint nearby star and a bright distant star can appear equally bright from Earth. You need distance to convert apparent brightness into actual luminosity. For nearby stars within a few thousand light-years, astronomers use parallax. As Earth orbits the Sun, nearby stars appear to shift position slightly against the background of more distant stars. By measuring this shift, you can triangulate the distance using basic geometry. But parallax only works for relatively nearby stars. Beyond a few thousand light-years, the shift becomes too small to measure accurately, even with space telescopes like Gaia, which has measured parallax for over 1 billion stars. For more distant stars, astronomers use other methods. If the star is part of a cluster, you can estimate the cluster's distance using various techniques, then assume all stars in the cluster are roughly the same distance away. For Stephenson 2, astronomers have used several approaches. One is spectroscopic parallax, which uses the star's spectrum to estimate its luminosity class, then compares apparent brightness to inferred actual luminosity. Another is kinematic distance, which uses the star's radial velocity and proper motion, its motion across the sky, to estimate distance based on models of galactic rotation. A third method involves studying the cluster as a whole. If you can identify enough cluster members and measure their properties, you can use statistical methods to estimate the cluster's distance. All these methods have uncertainties, which is why distance estimates for Stephenson 2 range from about 17,000 to 20,000 light-years. The uncertainty in distance propagates into uncertainty in the star's physical properties. If the distance is actually 18,000 light-years instead of 19,000, the star's luminosity would be different, which would affect the inferred radius. This is why radius estimates for Stephenson 218 have a range rather than a single precise number. Improved distance measurements would reduce that uncertainty. Let's explore what we can learn from the star's variability. As mentioned earlier, Stephenson 218 is variable. Its brightness changes over time. These variations provide a window into the star's internal structure and dynamics. The two main causes of variability in red hypergiants are pulsations and surface convection. Pulsations are rhythmic expansions and contractions of the star. The entire star swells up, then shrinks back down, then swells again. This happens because there is a feedback mechanism in the star's outer layers. When the star compresses slightly, the material becomes denser and hotter. Hot material is more opaque. It absorbs more radiation. The absorbed radiation heats the material further, causing it to expand. As it expands, it cools and becomes less opaque. Less opacity means less heating, so the material stops expanding and starts contracting again due to gravity. This sets up an oscillation like a spring being compressed and released. The period of oscillation depends on the star's size and mass. Bigger stars have longer periods because it takes longer for pressure waves to travel through them. For a star like Stephenson 218, the pulsation period might be anywhere from hundreds to thousands of days. By measuring the period and amplitude of pulsation, astronomers can constrain the star's mass and internal structure. Different models predict different pulsation behaviors, so observations can test and refine those models. Convection is the other major source of variability. Inside a star, energy is transported from the core to the surface by either radiation or convection. In some regions, radiation is more efficient. Photons diffuse outward, scattering off atoms and gradually carrying energy away. In other regions, convection is more efficient. Hot material rises, cool material sinks, creating circulation currents that transport energy. In red hypergiants, the outer envelope is highly convective. Giant cells of rising hot gas and sinking cool gas cover the star's surface. Each cell might be larger than Earth's entire orbit around the Sun. As these cells evolve and change, the star's surface becomes patchy. Some regions are hotter and brighter, others are cooler and dimmer. As the star rotates, these patches move in and out of view, causing brightness variations. If we could somehow get a close-up image of Stephenson 218, we wouldn't see a smooth, uniform surface. We would see a mottled, boiling surface with huge bright and dark patches constantly shifting and evolving. It would look more like the surface of boiling water than the smooth surface of the sun. Observing these variations over months and years builds up a picture of the star's surface dynamics. How quickly do the convection cells evolve? How large are they? How much do they affect the overall brightness? These details help astronomers understand convection at scales and conditions that can never be replicated in laboratories. The Sun also has convection cells called granulation, but they are much smaller, only about 600 miles across. Stephenson 218's convection cells are hundreds of millions of times larger. Understanding convection in extreme stars helps refine our understanding of convection in general, which is important because convection plays a role in many astrophysical contexts, from planetary atmospheres to neutron stars. Now let's talk about the role of rotation. Stars rotate, some faster than others. The Sun rotates once every 25 days at its equator, slower at higher latitudes because the Sun is a gas and different latitudes can rotate at different speeds. Massive stars on the main sequence often rotate much faster, some completing a rotation in just a few hours. This rapid rotation affects their structure, creating an equatorial bulge and influencing their evolution. Red hypergiants, by contrast, rotate very slowly. As a star evolves off the main sequence and expands, conservation of angular momentum should make it spin faster, like a figure skater pulling in their arms. But the opposite happens. Red giants and hypergiants spin slower than their main sequence progenitors. This is because they are losing mass through stellar winds, and that mass carries away angular momentum. As the star sheds its outer layers, it loses not just mass, but also rotational energy. The result is a slowly rotating bloated star. Stephenson 218 probably rotates once every several years, maybe even longer. This slow rotation has consequences. It means the star is nearly spherical, with little or no equatorial bulge. It also means that rotation doesn't significantly affect the star's structure or evolution at this stage. Contrast this with massive stars on the main sequence, where rotation can be a major factor. Rapid rotation can mix material between the core and envelope, bringing fresh fuel to the core and extending the star's lifetime. It can also create strong magnetic fields and drive stellar winds. But for Stephenson 218, rotation is a minor effect. The star's evolution is dominated by nuclear fusion, mass loss, and radiation pressure, not rotation. This simplifies the modeling somewhat because rotation adds complexity to stellar models. For slowly rotating stars, you can treat them as spherically symmetric, which makes the mathematics much easier. Let's think about the broader context of massive star evolution. Stephenson 218 didn't start out as a hypergiant. It was born as a massive main sequence star, probably a hot blue star, tens of times more massive than the Sun. It spent a few million years on the main sequence, fusing hydrogen into helium in its core. During this time, it was incredibly luminous, maybe 100,000 times more luminous than the Sun, and incredibly hot, with a surface temperature of 30,000 degrees Kelvin or more. It was a blue supergiant, not a red hypergiant. But as it exhausted the hydrogen in its core, it began to evolve. The core, now mostly helium, contracted and heated up. This contraction released gravitational energy which heated the surrounding hydrogen shell. The hydrogen shell began fusing, creating a new source of energy. The outer envelope, responding to this new energy source, expanded. As it expanded, it cooled, and the star transitioned from blue to yellow to red. It became a red supergiant. But the evolution didn't stop there. As the core continued to contract and heat up, helium fusion ignited in the core. This created even more energy, causing the envelope to expand even further. The star grew larger and cooler, eventually becoming a red hypergiant. At some point, probably in the near future, on cosmic timescales, the star will exhaust its nuclear fuel. It might undergo a final phase of instability, perhaps pulsating violently or ejecting large amounts of mass in eruptions. Some red hypergiants show evidence of episodic mass loss, brief periods where they eject huge amounts of material in eruptions lasting months or years. These eruptions might be triggered by instabilities in the envelope or by the ignition of new fusion shells in the core. Eventually, the core will collapse and the star will explode as a supernova. This entire evolutionary sequence, from main sequence star to supernova, takes only about 20 million years. That is incredibly fast by stellar standards. Compare that to the Sun, which will spend about 10 billion years on the main sequence before evolving. Massive stars live fast and die young, but their impact on the galaxy is enormous. Their strong stellar winds and eventual supernova explosions enrich the interstellar medium with heavy elements. They create new stars by compressing nearby gas clouds with their shock waves. They might even trigger the formation of new stars by their radiation pressure and winds. Many star-forming regions show evidence of triggered star formation, where the shock wave from a supernova or the radiation from massive stars compresses nearby gas, causing it to collapse and form new stars. So Stephenson 218, despite its short life, plays a crucial role in the galaxy's ecology. It is part of a cycle of star formation, element creation and renewal that has been going on for billions of years and will continue for billions more. Another aspect worth discussing is the comparison between different types of hypergiant stars. Not all hypergiants are red. There are also yellow hypergiants and blue hypergiants, though they are even rarer than red hypergiants. Yellow hypergiants are thought to be in a very brief transitional phase. They are stars that are either expanding from blue supergiant to red supergiant or contracting from red supergiant back to blue supergiant. This phase might last only a few thousand years, incredibly brief even by stellar standards. Because it is so brief, there are very few yellow hypergiants known. Rho Cassiopeia is one example, a star that has shown dramatic variability and mass loss episodes. In 2000, it dimmed by about 1 magnitude over a few months, apparently due to ejecting a large cloud of dust. Yellow hypergiants are unstable, sitting in a region of the Hertzsprung-Russell diagram called the yellow evolutionary void. This void exists because stars evolve through this region so quickly that they are rarely observed there. Blue hypergiants are at the other extreme, incredibly hot and luminous stars with surface temperatures of 20,000 to 50,000 degrees Kelvin. They are among the most luminous stars in the universe, outshining even red hypergiants, but they are also rarer and less well understood. Examples include Rigel in Orion, which is sometimes classified as a blue supergiant or blue hypergiant, depending on the criteria used. P Cygni is another famous blue hypergiant known for its strong stellar wind and distinctive spectral features. The star shows evidence of massive mass loss, with shells of previously ejected material surrounding it. Blue hypergiants are thought to be evolving rapidly, possibly undergoing dramatic changes over timescales of centuries or millennia. They might represent stars that are about to explode as supernovae, or stars that are transitioning to a different evolutionary phase. The exact evolutionary relationships between blue, yellow, and red hypergiants are still being worked out. Do all massive stars pass through each phase, or do some skip certain phases? Does a blue hypergiant always become a red hypergiant, or can it explode as a supernova while still blue? These are active areas of research. Observations of hypergiants in nearby galaxies, particularly the Large and Small Magellanic Clouds, have helped clarify some of these questions. The Magellanic Clouds are small satellite galaxies of the Milky Way, close enough that individual stars can be studied, but far enough that they provide a different perspective. Different metallicity, different star formation histories, different environments. Studying hypergiants in these galaxies and comparing them to Milky Way hypergiants helps astronomers understand how metallicity and environment affect stellar evolution. One key finding is that metal-poor stars, those with fewer heavy elements, tend to retain more mass and explode at higher masses. Metal-rich stars, like those in the Milky Way, lose more mass through stellar winds and explode at lower masses. This affects the type of supernova they produce and the remnant they leave behind. Metal-poor stars are more likely to leave behind black holes. Metal-rich stars are more likely to leave behind neutron stars. Stephenson 218, being in the Milky Way, has roughly solar metallicity or perhaps slightly higher. Its evolution and fate will be influenced by that metallicity. Let's also discuss the philosophical implications of studying stars like Stephenson 218. Astronomy has always had a philosophical dimension. Looking up at the stars makes us think about our place in the universe, about scale, about time, about existence itself. Stephenson 218 embodies some of these big philosophical questions. First, there is the question of scale. Humans evolved to understand scales relevant to survival. Distances of meters to kilometers, timescales of seconds to years. We are not built to intuitively grasp billions of miles or millions of years. And yet, through science, we can extend our understanding far beyond our intuitive limits. We can comprehend objects billions of times larger than anything in our direct experience. This is one of the triumphs of human cognition. We are not limited by our senses or our intuition. We can build instruments to extend our senses, telescopes to see farther, spectrographs to analyze light in ways our eyes can't. We can build mathematical models to represent things we can't directly perceive. And through this process, we gain understanding of phenomena far removed from everyday life. Second, there is the question of impermanence. Stephenson 218 is a reminder that nothing lasts forever. Stars are born, they live, they die. Even the largest, most impressive stars have finite lifetimes. And on cosmic timescales, those lifetimes are brief. 20 million years seems like a long time to us. It is far longer than human civilization has existed, longer than our species has existed. But in the context of the universe's 13.8 billion year history, it is a blink. The star will live and die in less than 1/5 of 1% of the universe's current age. It is a fleeting phenomenon. This impermanence extends to everything. Planets, galaxies, even the universe itself will eventually change beyond recognition. In trillions of years, all the stars will burn out, all the galaxies will drift apart, and the universe will be a cold, dark, empty place. Nothing we can see today will remain. Some people find this depressing, but others find it liberating. If everything is temporary, then the present moment gains significance. The fact that we exist now, that we can observe the universe in its current state, is remarkable. We are privileged to live in an era when stars still shine, when galaxies are still forming, when the universe is still dynamic and interesting. Third, there is the question of connection. Stephenson 218 is 19,000 light-years away. We will never visit it. No human ever will, unless some radical new physics is discovered that allows faster-than-light travel. And yet, we are connected to it. The atoms in our bodies were created in stars like it. The oxygen we breathe, the carbon in our DNA, the iron in our blood, all of it came from massive stars that exploded billions of years ago. We are literally made of stardust, not as a metaphor, but as a literal fact. And when Stephenson 218 explodes, it will scatter its enriched material into space. That material will eventually become part of new stars, new planets, maybe even new life. There is a cosmic recycling at work, a connection that spans space and time, linking all matter in the universe into a grand cycle. We are part of that cycle. We are not separate observers looking at the universe from outside. We are inside it, made of it, shaped by it. This perspective, sometimes called the cosmic perspective, can be humbling and empowering at the same time. Humbling because it shows how small we are, how brief our existence is on cosmic scales. Empowering because it shows that we are part of something much larger than ourselves, part of a universe that has been evolving for billions of years and will continue evolving for billions more. Our lives have meaning, not in spite of our smallness, but because we are part of this larger story. Now, let's think about the future of red hypergiant research. What will astronomers learn in the coming years and decades? Several new instruments and missions will revolutionize our understanding of these stars. The James Webb Space Telescope, as mentioned, is already operational and will provide unprecedented infrared observations. Webb's high-resolution imaging could potentially resolve the surfaces of nearby red supergiants, seeing individual convection cells directly. For more distant stars like Stephenson 218, Webb will provide detailed spectra revealing atmospheric composition, temperature structure, and variability. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters in diameter, making it the largest optical telescope ever built. With adaptive optics, it will achieve resolution far exceeding current telescopes. It might be able to directly measure the angular size of Stephenson 218, providing a precise radius measurement. The Square Kilometre Array, a radio telescope currently being built in Australia and South Africa, will be sensitive enough to detect faint radio emission from stellar winds and circumstellar material around hypergiants. This will help map the mass loss rates and wind structures in detail. Future X-ray missions will study the high-energy emission from hypergiants, revealing information about magnetic fields and shock waves in stellar winds. These observations will come from missions like Athena, the Advanced Telescope for High-Energy Astrophysics, planned for launch in the 2030s. Gravitational wave observatories, while primarily designed to detect black hole and neutron star mergers, might also detect signals from supernova explosions. If Stephenson 218 explodes as a supernova, next-generation gravitational wave detectors could potentially detect the gravitational waves from the core collapse. This would provide a completely new way to study supernovae, seeing directly into the collapsing core rather than just observing the light from the expanding envelope. Computer simulations are also improving rapidly. Modern supercomputers can simulate stellar evolution with unprecedented detail, tracking the nuclear reactions, energy transport, and mass loss in 3 dimensions. These simulations are revealing new insights into how convection works in hypergiant envelopes, how pulsations develop and propagate, and what triggers the final collapse. By comparing simulations to observations, astronomers can test and refine their models, gradually building a more complete understanding of these extreme stars. Let's close with a thought about perspective. When you look up at the night sky, you are seeing mostly main sequence stars. Ordinary stars, like the Sun burning hydrogen steadily. The hypergiants are there too, but they are rare and many are too distant or too obscured to see with the naked eye. Stephenson 218 is invisible to the naked eye, hidden behind dust and distance. But just because you can't see something doesn't mean it isn't there. The universe is full of wonders that are invisible to our eyes, but visible to our instruments and understandable through science. Stephenson 218 exists right now, 19,000 light-years away, a glowing ember larger than anything in our direct experience. It is shining, pulsating, losing mass, approaching the end of its life. In a few million years, maybe less, it will explode. The light from that explosion will travel through space for 19,000 years. It will arrive at Earth in our distant future, long after everyone alive today is gone. Maybe humans will still exist. Maybe they will have telescopes to observe the supernova. Maybe they will remember that their distant ancestors studied this star, predicted its fate, understood its nature. Or maybe humanity will be gone and the supernova will blaze unseen, except perhaps by other intelligent species elsewhere in the galaxy. Either way, the explosion will happen. The laws of physics don't care whether anyone is watching. The star will complete its life cycle, scattering enriched material into space, contributing to the ongoing evolution of the galaxy. And that material will eventually become part of new stars, new planets, maybe new life. The cycle continues. For now, we can study Stephenson 218 from afar. We can measure it, analyze it, understand it. We can appreciate its extreme scale, its brief life, its crucial role in the cosmic ecology. And we can marvel at the fact that we, tiny creatures on a small planet, can comprehend something so vast and so distant. That's the power of the human mind. That's the gift of science. That's what makes us uniquely capable of understanding the universe we find ourselves in. Stephenson 218, the largest star ever discovered, is a testament to the universe's capacity for extremes. It is a star that pushes the limits of size, luminosity, and instability. It is a star that challenges our models and expands our understanding. It is a star that reminds us of the vastness and diversity of the cosmos. And it is a star that connects us to the larger story of matter's journey through space and time. Thanks for joining me on this exploration of the largest star in the universe. If you found this journey as fascinating as I did, consider liking the video or subscribing to the channel. It helps these stories reach more people who share our curiosity about the cosmos. And remember, the next time you look up at the night sky, somewhere out there in the constellation Scutum, invisible to your eyes but real nonetheless, Stephenson 218 is shining, a cosmic giant living fast, burning bright, and preparing for its final magnificent act.